All right, guys. Hey, welcome back to another lesson. Triangles. Well, think about what do you know about triangles? Hopefully, you know some things about it up to this point. So the first, I would say this first lesson will be a good review as to what you should know about triangles. The second part of the lesson, the exterior angle theorem, might be something a little different, but we're going to go through some foundations. And then at the very end of the lesson, we're actually going to prove that there are 180 degrees in a triangle. Okay? Dun, dun, dun. Using like a T-chart method like we did in the previous proofs. But we will do that. But other than that, just make sure a piece of paper and let's get to it. All right? So classifying a triangle, well, before we get into actually classifying it, let's talk about just the different parts of it. I think it should be pretty self-explanatory. We have three vertices that are A, B, and C. They're points. The sides of a triangle are line segments. So in this case, we have side AB, BC, and CA. Okay. And remember, you're allowed to switch when it comes to line segments. The order doesn't matter. And then, of course, we have the angles A, B, and C. Or using a three-point method, you can call it angle BAC for angle A, or CAB. Remember, you can go in the reverse order. ABC or angle B, angle BCA or angle C. Okay. Now we'll say when we get to more, complex shapes where there's a bunch of triangles inside of a larger shape, you might want to use the three-point method to naming these angles. That'll be a little bit easier to identify. Okay. All right. Now this is by the angles, right? We're going to classify the triangle by its angles. So we have an acute triangle, which has three acute angles. If you remember, acute means less than 90 degrees. We have an equal angular triangle, which is three congruent acute angles. Now, break the word down. It makes it a lot easier. Equal angular. You hear the word equal in it, and you hear the word angle. So equal angles. Okay, so all three angles are the same. Now, let's think about it. Let's go a little further. If all three angles are the same, and if you remember that there is 180 degrees in a triangle, what does each angle have to be? Well, I think that has to be, 60 degrees, right? 60, 60, and 60, all add up to 180. Obtuse triangle, you have one obtuse angle. Can't have more than that because it goes past the 180-degree margin. And the last one, a right triangle, which has one right angle, and that's what this little box is here for. Remember, that box means 90 degrees. Okay, let's go to sides. Equilateral triangle, okay, has three congruent sides. Once again, break the word down. Equal, you can hear in it. Lateral means side, so equal sides. A isosceles triangle has at least two congruent sides. You could claim that this is an isosceles triangle because it has two congruent sides, right? So you can make the statement that all equilateral triangles are isosceles. You could go into that logic if you like. And then the last one would be scalene triangle. That has no congruent sides whatsoever. All the sides have some sort of different measurement. Okay, so that's a review of what I would hope, have heard up to this point. Okay, just classifying it by its sides and its angles. So for our first example, classify these guys as either acute, equiangular, obtuse, or right. So we have three options there. So let's see, the right triangle, well, if I take a look at it, I can see that all the angles are less than 90. So that classifies it as an acute triangle. So that would be an acute triangle for that guy. Okay. For this guy, we have 60, 30, and 90. Well, it's not acute because it's a 90-degree angle in it. Acute's less than 90. It's not obtuse because you don't have an angle bigger than 90. And it's not equiangular because they're not all the same. It's actually a right triangle because there's a 90-degree angle involved. Okay, last one. Doesn't look like much, but if you look at the very bottom, this angle is 97 degrees. That's just large enough to be classified as an obtuse triangle. Okay, so the gold triangle there would be obtuse. And that's just classifying it by its angles. All right, let's do some calculation. So for the first one, the measure of the sides of an isosceles triangle ABC are given, and we're supposed to find that measure. So here's the deal. I need to know what x is before I figure out what the measurements are. Now, I can see that from these congruency lines, these little tick marks, that this side is congruent to this side. And that makes sense because this is isosceles, which has two congruent sides. So what I'm going to do is I'm going to set AC equal to BC, okay, because they're congruent. So here's what I'll do. Up at the very top, I'll say they're congruent sides. Because they're congruent, they're equal in measurement. So 4x plus 1 equals 5x minus a half, since they are the same. So for instance, if this was like 10, this is 10, right? So if the measurements are the same, the equation is going to be the same. Before I finish solving it, a lot of people ask, well, wait a minute, what about this 9x minus 1? What do I do with it? Nothing. You do nothing with it. It's just kind of hanging out there, it's chilling. But the reason why we don't use that is because, well, for an equation, we just need two sides. We only are going to use the two sides that we know information about, and we know these are the same. I'm going to use this guy to figure out what this measurement is once I know what x is. Okay, so I'm going to ignore that for right now. All right, combine terms. Get the x's to one side. Okay, so subtract the 4x. And then to get x by itself, I'm going to add the half. So 1.5 is going to be x for that guy. All right. Now, that's great, but it wants me to find the measure. So I'm going to have to plug this back into each one of those guys. So let's see. Let's plug it in for AB first. So 9 times 1.5 minus 1. Okay. So 9 and 1.5 is what, 13.5 minus 1. So AB is going to be 12.5 for that guy. Okay. Now, let's look at AC next. So we have 4 times 1.5 plus 1. Once I substitute that in. So 4 times 1.5 would be what? Be 6. Plus 1 would give me 7 for that guy. Now, here's the deal. AC and BC should be the same measurement. I know that already. So BC should be 7. If it isn't, then I did a mistake and I have to go back and check my work again. So 5 times 1.5 minus a half. So 5 times 1.5 is 7.5 minus a half. Hey, how about that? We did it correctly. All right? BC is going to be equal to 7. So once again, when you see problems like this, I mean, I know you're probably thinking, are we ever going to use this in the real world? Always asked. No, you're not going to have, a measurement where there's a lot of algebra involved, like this, okay? You're not going to have x's and stuff like that. You're going to sit there and say, if this is 10 centimeters and this is isosceles, that's 10 centimeters. I'm done. Yeah, I get that 100%. The algebra is just trying to review what you did in previous math years. It's just keeping your logic, keeping your calculation mind sharp. Okay, so I get that. All right, don't sit there and say, this is just another useless lesson. It's not. Okay, I promise you, I get it. Trust me, I do get it. All right, next one. Example 3. Find the measurement of this equilateral triangle FGH. So we're going to do the same thing. We got to figure out what y is. And then after we figure out what y is, we have to plug it back in to find the measurements. All right. Doesn't sound like a monumental task. I think we could do this. So equilateral, I need to know what that means. And remember, if I break the word apart, equilateral equal sides. So that means each side is the same measurement. Now, because of that, what I could do is I could pick any two sides I want and set them equal to each other. Okay? So since that's kind of like your option, you might as well pick the two equations that look the simplest. Now, they all kind of look basic, but since this negative 19 is here, I'm not going to use it. I'm going to use the smaller numbers. So I'm going to set these two guys equal to each other. But what I want to do, and this is good for your notes, put down that all sides are equal. Therefore, that's what that symbol means. Therefore, the 3 dots, pick any two sides and set them equal to each other. I think what's very important is that anytime you're taking notes in a math class, you should always leave yourself a little bit of a breadcrumb trail, just a little bit of English. Like, why are we setting these equal to each other? Okay, I should have done it in the last example, but I want to make sure I do it for this example. So I'm going to say that FG, okay, I'm just going to skip the equals. FG is equal to HG. I'm not going to go congruent and equal. I think we're okay for now with that. So 2y plus 5 equals 3y minus 3. The most complicated thing I've seen students come up with is they're trying to make all three of these expressions in one equation. You can't, okay? You just pick any two you'd like because it is equilateral all sides. I've seen some people in the past do this. And first off, that's not logical, okay? You can't have two equal signs and an equation like this. So just don't get it in your mind that when you see all this algebra here, I got to use all of it. No, you don't. You only have to pick the parts that you need specifically. So let's go ahead and solve it. So I'm going to get the 2y to the other side by subtraction. So those cancel. Gone. 5 equals y minus 3. Add the 3 over. Sorry. Y is going to be 8 for that guy. Now I'm not done. I need to plug the rest of them back in. So FG, FH, and GH. Okay? So here's the deal. When I plug these in, and this is what you got to think about, don't just plug stuff in without thinking what you should see. All right? When I plug these in, I should see that all of these sides are the same measurement because it's equilateral. So let's see if it works. So 2 times 8 plus 5. So 2 times 8 is 16, plus 5 gives me 21. Let's see, FG, that was FG, I'm sorry, FH would be 5 times 8 minus 19. 5 times 8 is 40, minus 19, 21. And then GH would be 3 times 8 minus 3. So 3 times 8 is 24, minus 3 is 21. Hooray! It works. Okay. So that's the key. All sides are equal. Okay, so you pick any two sides you want. Now I could have picked these two, set them equal to each other. I'm still going to get y to be 8. And I'm still going to solve for the rest of it. Okay. All right. I think this looks pretty good so far, huh? Any questions, thoughts, concerns, dilemmas? I don't know if I can hear you through here. You can try. You can shout at the screen. No? Okay. We tried. All right. So what I'm going to do is I'm going to jump into this segment here. I'm going to skip that example and I'm trying to keep the video as small as possible. So we have here the triangle angle sum theorem, okay? The sum of any, I'm speaking ahead of myself, the sum of the measures of the angles of a triangle is 180, no matter what the triangle is. They're always going to add up to 180, okay? And at the end of this lesson, we're going to prove that together. But for right now, let's just use that basic fact to help us solve for this guy. Okay? And remember, you can pause the video to write down these examples and work them out ahead of time. See if you come up with the same conclusion as we do. Okay? All right. I want to figure out what angle 1, angle 2, and angle 3 are. I want to know what their measurements are. Currently, I don't know. So looking at this, I don't want to look at this triangle because it has 2 unknowns in it. And that's going to be, well, no bueno, okay? I'm not going to be able to work with that. If I look at this triangle here, I have 1 missing measurement. That's a little bit easier to work with because I know that all 3 of these add up to 180. So what I'm going to do, and I'm just going to write this out algebraically. I know you can do the calculation in your head or use a calculator. I get that. But for your notes, it's probably a good thing to write down. So I know that the measurement of 1 plus that 43 degrees and 74 degrees equals 180. Okay, that I do know. So what you're going to do, and this is what you would do mentally in your head too, is that you would add these guys and subtract it. I can't talk. And subtract it from 180. Okay. Well, when we do that, we get what? This would be what? 117 Subtract it from here, I think it gets 63 degrees left. So the measurement of 1, that's a bad way to write. Let me try that again. The measurement of 1 equals 63 degrees. Now notice something here. These triangles are being formed by these two lines crossing. And what's interesting is 1 and 2 do have a relationship to each other, okay? If you remember back in your first couple lessons in geometry, these are called vertical angles. And we know that vertical angles have the same measurement. So I'm going to say that the measurement of 1 and the measurement of 2 are the same because they are vertical angles. So the measurement of 2 is also 63 degrees. Now once again, I'm writing this down so you can follow it step by step, write it in your notes. I'm completely fine if you just, writing through it and just say, oh, this is 63 degrees. I get that. All right, now let's look at this. Now this triangle, we know this is 63, that's 79. To figure out angle 3, well, I think I need to add those two angles and subtract from 180 because once again, 180 degrees in a triangle. So the measurement of 3 plus the 63 degrees that we know, plus the 79 degrees that's there, adds up to 180 as well. Okay? So we're going to do the same thing. We're going to add these two up, subtract it from 180. Okay? And we get what? This would be, I think it'd be what, 151? Am I right with that? 151 with that? 63 and 79? Nope, 152. So then if I subtract it, we get 38 degrees for that guy then. So this would be 152 degrees. Okay, subtract from that. Not 152. Oh my goodness. 142, sorry. Addition error. And we subtract, we get 38 degrees. And we're done. So we're just using the basic fact that there's 180 in a triangle. Okay, and by doing that, we can figure out the other measurements. Let's do one more. Okay, and once again, I encourage you, pause the video, try them out, see what you can come up with. I have two triangles. Now, this is not drawn to scale, just like in the previous problem, not drawn to scale. Okay, just drawing these on this PowerPoint was interesting enough, and clicking and dragging. I know there's probably an easier way of doing it, but at the time when I created these like 5 or 6 years ago, I did the best I could. So this is not drawn to scale. Looking at both of these shapes, you want to look for the triangle that only has one missing measurement, because that would be the easiest to solve for. It would be this triangle here, triangle KML. So this is 57, this is 71. I can figure out angle 2 by just doing a little bit of subtraction. So looking at just triangle KML, I know the measurement of 2 plus the 57 degrees plus the 71 degrees equals 180. So this is 128. When I add them, if I subtract it to the other side, the measurement of angle 2 is what, 52 degrees? For that guy. Now, we could have tackled this one first as well, and there's a reason for that. Look at angle 1 and 57. Going back to what you did initial stages of geometry, you know that 1 and 57 are supplementary. They add up to 180. The reason why they do that is because they're linear. If you remember from a long time ago, linear angles are adjacent to each other, and the non-adjacent sides are rays, right? They go on forever. Now, I know it's in a shape, but if I were to block out most of the shape, I could see that picture that we used from a long time ago. So if they add up to 180 degrees, all I have is a little bit of subtraction. So the measurement of 1 plus 57 equals 180, and that's because they are linear angles. Okay, that's the reason for it. Now, for right now, I would, in your notes, you still want to write this down, but this is going to be very helpful when we start talking about triangle proofs. Okay. All right, do a little bit of subtraction. So the measurement of angle 1 would be 123 degrees. A little bit of subtraction. That's all this entire process is This is nothing but subtraction, over and over again. Okay, the last triangle we have is what? JKL. And in that triangle, I need to know what the measurement of 3 is. But if I add it up with the 28 degrees, and now we know what angle 1 is, which is 123 degrees, it should come out to 180. So what I'm going to do is I'm going to add these two together. Okay, subtract it from 180. Okay, and when I do that, I believe this comes out to be what, 151? So if I subtract that, I get what, 29 degrees? That final product. Not product, I don't know why I use that word for that final answer. I should have said. Okay, so that'd be 29. That's it. Please take note that the stuff we learned in the past, vertical angles, linear angles, okay, they all come into play. So you can't forget that information. All right, it's going to be very beneficial to you. Now, I believe the next slide is the exterior angle theorem, which we're not going to do right now. Okay, that's a future lesson, future episode. Okay, what I want to do for you right now is we're going to prove that there's 180 degrees in a triangle. And I'm going to show you a T-chart way of doing it, and I'll also show you a visual way of seeing this. Okay? So that's what we're going to do for both of these. Let me just get rid of the video here. Not rid of the video, rid of the PowerPoint. Okay. And what I'm going to do is I almost said scroll. I'm going to move the screen a little bit closer so you guys can see this a little bit better. Just like that. Okay. And now I would highly encourage you to write the proof down yourself. There are some things in this proof that we haven't really done before, and that's fine. It's great information for you to have just for future reference if you do more proofs in the future. So here's what I'm going to do. Okay, my first step, well, it's always a list of the given, right? So our given is we have a triangle. It's ABC. Boy, that's a lot of information, isn't it? It's not helping us anymore, but that's a lot of info. So what I'm going to do is I'm going to do a little bit of construction. Point A, I'm going to draw a line that's going through point A, and it's parallel to BC. Okay, so that's what I'm going to do. So a little bit of construction. And think of it this way. When I create that line, we'll make this, what, point D. We'll say there's a point out there. Just something for reference. The one thing I want to note, I don't want you to feel like I can do this randomly. No matter what point is drawn, you can always draw a line that's parallel to it, right? You can always draw a line that intersects that point and is parallel to any other line, okay? That can, construction-wise, we can do it, okay? And we'll talk about that when we do more constructions in the future, that is something that is possible, all right? It's not impossible. So, not that you would ever see this in one of your proofs in the future, but this is a nice little construction step. So we're going to draw a line AD through point A, and it is parallel to BC. Now I did a lot of abbreviations there so I could fit it all, okay? So draw a line AD through point A, and it parallel to BC, okay? So what I'm going to do is, that's called the parallel line postulate. I believe it's called parallel line postulate. It's a parallel postulate. I don't know if the line's part of it or not, okay? But construction-wise, we're actually going to be doing more and more of those in the future, so it's coming. So now what did that do? Well, first off, let me go ahead and number. Now we have these angles that come into the picture, right? So we're going to keep that in mind. But here's the goal, okay? The reason why I drew that, I want to come up with an equation that adds it to 180 degrees. And then whatever is in my equation, I'm going to substitute what I want and get rid of what I don't want. Okay, we did that before when we did parallel line proofs. Same thing here. I want to have an equation to start with, and then after, get rid of the stuff I don't want in that equation and put stuff I do want. Okay? So by doing that, look what happens. The measurement of 4 plus the measurement of BAD. Okay? If I look at those guys, and actually, we'll put this step in like this. They're supplementary, right? This angle and this entire angle over here, and I'll tell you what, let me zoom in a little more so you guys can see it a little bit better. And this entire angle over here adds up to 180 degrees. So they're supplementary, okay? And that's because that's how we define a linear pair of angles, okay? Now, because they're supplementary, I can add them up to 180. Just like that, okay? And that's just definition of what supplementary means. And once again, I am abbreviating DEF for definition. Now you're probably asking, okay, this doesn't look like this. In fact, this looks even further away from it. We're getting there, okay? Here's what I'm going to do. I need to define what BAD is. Okay, because BAD is not in here. I want to actually put down what BAD is, which is what, 2 and 5? The measurement of 2 plus the measurement of 5. And that, if you remember from a long time ago, that's the angle addition postulate. Okay? We talked about the angle addition postulate in the beginning of this course. So now what I could do is I could take this information and I could substitute it in this original equation that I have. So the measurement of 4 plus the measurement of 2 plus the measurement of 5 equals 180, and we got there by substitution. So far, so good? Now, here's the cool part. This doesn't look like this. What do I want to get rid of here? I want to get rid of the 4, and I want to put 1 in its place. I want to get rid of 5 and put 3 in its place, right? Okay, I can do that. Think of it this way. See how these guys are parallel to each other? And I'll include the arrows so it's easier to see visually. Because they're parallel, 1 and 4 are the same. Okay, 1 and 4 are alternate interior angles. If you remember that picture from a long time ago, I'll just erase over here, okay? We're seeing this. These guys are the same. Okay, if I were to extend this line, okay, and extend the bottom line, I'm going to get this picture. So I'm going to say that the measurement of 1 equals the measurement of 4, and that's because they're alternate interior angles. Now what I'm also going to do is include angle 5 and angle 3. I'm going to put 2 arcs there so they're not confused with the other ones. So I'm going to write that down in this step as well, because they're also alternate interior. Okay, same reason. All right, now I'm out of room. I gotta change some things up here. So over here, I'm gonna finish it. Okay. So because of that, this is my statement, my reason column. Okay. So now what I could do is I could swap out 4 and 5, okay, for 1 and 3, because they are the same measurement. So I could say that the measurement of 1, the measurement of 2, the measurement of 3 equals 180, and that's by substitution. Proof is done. I just proved that there's 180 degrees in a triangle. Now, you're probably thinking this too. You're like, well, wait a minute. Why does this work for all triangles? Because it seems like we just made it specifically for this little acute triangle here. I get that. Think of it this way. No matter what triangle I draw, I can still draw a line that's parallel to one of the bases. No matter what orientation, no matter how I draw it, I can still come up with a way to draw a line that's parallel to that base. And when I do that, I create alternate angles every single time, okay? Which allows me to interchange the angles to make it equal 180 degrees. And it's not to make it equal, it is equal to 180. And this little T-chart is showing that. Now, the last thing I'm going to do is something visual. And I know this video is probably very long already. You could do this at home. But if you cut out a nice triangle piece of paper, just like this, we're going to prove that it's 180 using this visual aid. Now, here's one thing I want you to think about. What else is 180 degrees? All right. Well, a line. Isn't a line 180 degrees, right? So here's what I'm going to do. I'm going to take this, and I'm going to fold it down. I'm going to fold this angle to the very bottom of the triangle here. I'm going to take this angle,
fold it in. It's going to meet where A is. I'm going to take this angle and fold it in to meet where A is as well. Now look at all three angles. All three angles, okay, oops. It's kind of hard to hold all of these. But all three angles are on a line, right? All three angles, because they're on a line, they're supplementary, they add up to 180. And I could do that no matter what the triangle is. I could fold all the angles in to fit on a line like this. Okay, so here's the original triangle again. And if I fold all the angles down, they stay on a line, which makes it 180 degrees. Okay, so I don't know, nice little visual to show you too, that it's not just some algebra mumbo jumbo that shows this. It's actually it's a proven fact, just a nice visual way of doing it too. There's other ways out there to prove it, but those are just two ways to go about it. So anyway, this video is already long enough. It's like 30 minutes. So I do apologize because the proofs at the end took a little bit more time. So have a good day, guys, and I'll see you in the next lesson.